I hope people are finding these lectures interesting. And today is the last lecture I'm going to deliver, which we consider just a kind of review period, like review of techniques. And then starting on Friday, we'll look in a bit more depth at specific material types where there's heterogeneity is present on a kind of mesoscale. And this can get into the idea of wave dispersion, wave trapping, this kind of phenomena. So hopefully that will be interesting and fall very strongly into line with the basic theme of this collaboration. So hope that's okay. So Oleg, are you okay if I start?
Yes, please, Bill. We are waiting with great interest.
Okay, okay, thank you. I'll share my screen like yesterday.
Yes.
And what I'll do is I've got some movies and I'll play them as when we get to the appropriate point. This is a very visual set of presentations, visual in the sense of it's a lot of imagery, photography, etc. And I've got lots of high-speed videos, but I'm going to show mainly 3 or 4 which cover the ground in a little bit more depth. Okay, so hopefully we can see a bit more of the fundamental mechanics that are occurring in the system. There's lots of very high-speed images there.
Thank you very much. Thank you.
Okay, okay, great. So I'll share screen now. So this is the one I shall share. I should go PowerPoint. So hopefully that's good and you can hear me. So in the first tutorial, we talked a little bit about waves and wave transmission and the effective interfaces. In the second one, mainly gauges and the use of gauges to measure internal states in material. A brief mention of optical velocimetry at the end of the lecture. Again, all looking very much at individually small regions within a material and small and velocities varying along a axis, along a line going from the surface towards the probe. However, in a lot of situations, we're dealing with heterogeneous materials that have very strong variations in density, chemical composition. And often we approach these materials in different ways, different theoretical ways, and it is useful to have techniques that allow us to see what is happening over a larger area of the sample, internally, externally. Doesn't really matter. We really need to see what's going on. And so that was what I talked about yesterday, gauges and visor. But here we're going to talk about 2-dimensional and 3-dimensional fields that we're measuring within a target. And we try to get diagnostics to work together at the same time. So one thing to remember, often it doesn't make too much of a difference, but depending upon the accuracy you're thinking about, then we've got a camera or some kind of optical device which is recording from a fixed position, and the sample and the impactor move through the field of view. So effectively, the camera is acting in a Eulerian frame of reference. The camera view is fixed, the material moves through it. When we have a gauge is embedded within the material and moves with the material, and therefore we're in a Lagrangian frame of reference. Given in shock wave impact, the very fast nature of the events on microseconds, the movements we're talking about are of the order of a few millimeters on the time scale of the experiment, meaning that the difference between the Eulerian and the Lagrangian frames of reference may not be terribly significant. There'll always be a difference, but it may not make a huge one. However, as we go to larger targets and events which take much longer, then the difference between the Eulerian and the Lagrangian frames of reference may have a significant effect upon the analysis. So this is a review of some of the techniques that myself and my colleagues and others have used, looking at high-speed photography, and then in a little bit more detail going forward through what people are doing currently. Framing photography, very old technique. High-speed cameras have now been around in one form or another for getting on 100 years. Even the fully electronic ones, electrical electronic ones, have been around for 100 years. Then we're going to look at some techniques we apply to the system, optical techniques, Schlieren shadowgraph, etc. And then very much more in the modern world, there is in the 21st century a large emphasis on image correlation techniques. And the main question there is being able to get the data on sufficient spatial and sufficient temporal time, temporal detail. So I'll just start off with some images that I took with a student 20 years ago. And basically, it's a thin bed of explosive. We're looking at the back of that disc of explosive. That disc is about 12 millimeters in diameter, and it's about 0.5 millimeter thick. And we have impacted it. And this is using a camera which was able to capture images with an exposure time of 30 nanoseconds and an interframe time, IFT, interframe time of 0. So basically, the first image represents 0 to 30 nanoseconds after the camera was triggered. The next image, as you go along the top, is the next 60 to 90, 30 to 60 nanoseconds. The third one, 60 to 90. You can do the sum from there. So what you see there is an initial impact, and you can see some areas of brightness, areas of kind of a yellow color in the first image, which spread in the second image, and in the third image there's quite a lot of what is indeed chemical reaction occurring in the system. And then in the fourth frame and the fifth frame and onwards, the intensity dies away as the reaction drops due to pressure being released from the system. So with modern high-speed cameras, you can look at individual grains of, say, an explosive, individual grains of a material, and look at them with very good time resolution. And in this case, you can see hotspots forming within that explosive bed and get an idea of how they communicate with one another. Again, it's a kind of data which can be used to validate models of reaction and growth in materials. But we can actually do something more advanced than simply looking at light intensity. We can illuminate the system and look for things like changes in density within transparent medium. And this led to two really early visualization techniques, shadowgraph and Schlieren, which use a light source. Maybe it's a flash illumination, maybe it's a laser illumination. Basically putting in a few 100 joules of energy, maybe 1 joule per microsecond of illumination, and you have to set up the system to ensure that the light source is even and columnar. So you've got a nice completely unfocused light source giving even illumination. And that is, again, where you want to have some experimental knowledge, experience, set up that system. And there are a couple of, here's a couple of theoretical points. If you're wanting to measure displacement, then shadowgraph tends to be the best technique, and it's sensitive to the second differential of the refractive index of the material. You can find that in many optical textbooks. If you do Schlieren, it's the angular deflection you're measuring, angular deflection based upon the differential of the refractive index. And if you're doing different forms of interferometry or some forms of correlation, then the phase difference is the important thing you're after, and that's directly dependent upon the refractive index. So you have different techniques which record different levels of detail of the change in the material properties, of the change of the refractive index, and refractive index is very strongly dependent upon density. So this is a standard shadow graph setup. We have a flash source there, a lens to make a nice columnar and even illumination of the target, and the green in the middle is the target, and then over on the right hand side is a blue area which represents the image. And when we impact the bottom of the green target, we cause a wave to run through it, and that wave is associated with a change in density. And because there's a change in density, you can get some deflection of the light from it. And what we see in the lower image is that at the top of the image, the light goes straight through. There's no change in refractive index on the path of that light moving due to the wave. On the bottom, it's behind the shock wave, behind the impulse, and everything is even. There's no change in refractive index there. But the beam of light that goes where the wave is passing experiences two different densities of material. There's an interface there caused by the wave, and that causes some refraction of the wave. And what you get is a movement of light from one area of the image to another. So on the blue side, you can see a white line where there's slightly more intensity, and a black line where there's lower intensity. That's shadow graph. Very easy to set up experimentally. The main thing is getting the timing of your camera and the illumination to work correctly. This is Schlieren. Schlieren is a little bit more different. Schlieren is a German word, which I've tried to have multiple Germans explain to me in English because we have no equivalent word. Basically, if you imagine, seeing as it's cold in Perm at the moment, you can do this experiment. You have a frosted window, so you have some window that you've breathed on. There's a kind of mist there, and then you rub your arm across that window to kind of clear it, and you leave these streaks behind. That's called a Schlier, apparently. So what we have in Schlieren is similar setup at the beginning. We have a flash lens sample, but on the other side, we now have a second lens, which is focusing the light down to a point, and then a third lens to again expand that light out and make it more columnar. And what happens is that we introduce a knife edge to remove approximately 50% of the light intensity. So we're cutting off basically the bottom half of the light that's being focused. What this means is when we have the wave moving through the material, the light that is being refracted, in this case refracted down, does not get to the camera. So what this means is you don't get that extra brightness, you get the areas that remain a little bit dark. This enables you to see what is happening in a little bit more detail. And we have a couple of images to compare here. The first one is a shadow graph of an experiment, and the lower one is a Schlieren of more or less the same experiment. In the top image with shadow graph, you can see the big change in the wave. There's a nice black curve showing where the shock front is in the air. And you can see there's a little bit of detail around what's going on in the bullet. And then as we go to the lower image, we can see in a lot more detail the turbulence and flow and other waves coming from the target. We can also notice that the wave, the initial sonic boom, the shock wave moving through the air, is not so strongly marked. It's a very obvious black line in the shadow graph. It's a change in the intensity of the grey in the Schlieren, but other waves are more noticeable. So depending how your optical setup works, you can detect those waves in greater or less detail, and to a certain extent you can choose which type of variation you're looking for. So Schlieren good for very gentle variations in waves, and shadow graph's good for detecting only the really strong waves in the system. So high-speed photography, we looked a little bit at framing there, very common technique. Having a look at streak photography, and Many people will be in this lecture, I hope, are very, very familiar with streak photography. So here we have a target with a wave moving through it at a velocity u. And if we were taking framing images, we would have 3 images at time 1, time 2, time 3. If instead of just doing it like that, we just looked upon a single line down the target through a slit, and we were willing to sacrifice the 2-dimensional field of view to look at a 1-dimensional line, but with how it varies with time, that would be a streak image. And on the left-hand side there is the idea of the individual frames, and on the right-hand side is a kind of streak image. The vertical axis represents distance, and the horizontal axis represents time. And it's very good for measuring velocity or variation in velocity in material. So this is an example of a streak image, and this is of a failure wave, actually going through a system, going through some glass. We have the impact direction is on the left-hand side, and the waves are going to move to the right through the image. And the dark line at the bottom of the image is the initial shock wave, and it's marked as shock. That wave reaches the rear of the target about halfway up the image, and there is a reflection occurring. Now, behind that shock, you can see over a time period of a couple of microseconds or so, you can see other waves developing in the system. Other processes are happening in the system. We can see a kind of dark region behind the shock wave. We can see a kind of very cloudy region as well developing. So processes such as the growth of that failure wave are occurring, or failure front are occurring in that region. So this is the initiation of the failure wave, and here the failure wave is getting very strong. Now, at some point, it all goes very black because of all the cracking in the sample, and we don't see very much. So we lose detail, but at least we've seen the velocity of the shock wave, the reflection, and got an idea of the velocity of that failure front. So streak photography and framing photography are quite useful. However, if we start thinking about other forms of experimental techniques, speckle is a very common experimental technique. And we could do a speckle pattern by illuminating a rough surface with a laser. And you will get different reflections, small different reflections of the laser on that surface. And you'll get regions of brightness, regions of darkness. So you'll have this kind of a speckly, boiling kind of reflection from the surface. And what you can do, and this is using what these days, and for some people in these in this lecture, will be very old-fashioned film, actually physically using a film and a laser illumination of a target. And what happened was we had the target, we flashed the laser without putting any impact or anything onto the target, and captured the speckled image. And there we have it, a single exposure speckle pattern, just an image taken from some laser illumination of a surface. We then, without moving the film, without moving the camera, we then impacted the target and took a second image. And this meant that we got a point that was displaced because the speckle had been displaced by the impact. And what we can see on the right-hand side is that displacement vector, and there's a scale there showing the kind of distances we're talking about. So we've got these points, and they're all close together, and they've all moved in a certain direction. Then, and what I think is very nice about this is almost like a university level practical experiment. We then shine a laser through the speckle photograph, and because we have these 2 points there, it's acting very much like a diffraction pattern. And so you get a diffraction pattern coming out from that laser illumination of the film. And the spacing of the diffraction pattern gives you information upon the displacement, and the angle of the fracture pattern gives you an idea of the direction of that displacement. So that's a very simple technique. It requires a flash laser and a single static camera. It does not require huge amounts of investment, but of course you need a laser that you can pulse. And you can do a Fourier transform of those images if you're feeling that way inclined. Find the peak of correlation, the peak of motion of the movement in the system. The big spike in the middle is the initial illumination, but those 2 points either side represent the displacement seen in the image. They give you the magnitude of the displacement. A warning here, this type of technique does not give you any independent idea of the direction of motion. It only gives you the magnitude and the line direction upon which that motion happened. It doesn't tell you if it's going forwards or backwards, but it tells you along that line, this is the direction of motion, forwards or backwards. If you set the experiment up, generally you have a good idea what the direction of motion is going to be. So you bring some extra knowledge into that analysis. So here we have a crack. This is an image of a crack. And I'll just get this cursor on the screen of a crack growing through a block of material, transparent perspex polymethyl methacrylate block. The crack is growing, and the double pulse experiment was done, and these dots here show the diffraction patterns as we go along this line going down the image, and you can see different amounts of different widths of the diffraction pattern, and also different angles. And this gives us a good measure of the displacement around it. And if you spent time, this is very early 1990s here, if you spent time, you could work out the direction and shape of the motion around that crack tip in relatively good detail. Now, you can think about speckle photography. It's widely applicable, so you can do it on many surfaces. It's quite complicated post-processing. And there is this, you don't know which direction the motion is, you just know its magnitude, and you don't know if it's a positive or negative displacement. You know the direction and you know the magnitude, but you do not know whether it's a positive or negative displacement. And there are many modern alternatives which have been developed over the last 20 years or so, involving digital speckle pattern photography, which use cross, meaning you compare one image to another, rather than this, which is called autocorrelation, meaning that the information is contained within one image. So that's one set. Now we've got another series of techniques called grid techniques. Again, this is an example where cross correlation becomes more important. So fine grid method, you can measure the whole field in plane displacement. It's a simple technique, and again, you can put it onto many surfaces. And here we have a system where we have a propellant grain, and we're going to crush it. And we're going to measure the crushing of the sample. We're going to measure force versus time, and you can see we've got those lines on it. So the data we get shows images like this, where we have the grain with the holes and the horizontal lines on it. But taking images like that, we have to do some further processing. We have to look at the images and get an idea, but we really should be measuring stress and strain against each other versus time, coming up with these strain maps. So we have to do a lot of filtering here. So first we do spatial filtering. These techniques can be looked up in many textbooks. They're very common techniques in the world of image analysis. But you do spatial filtering to eliminate in one case, the horizontal lines, and the other case to eliminate the vertical lines. So we end up with the top image, which is the vertical lines only, and the lower image on the right-hand side, which are the horizontal lines only. And you've got these two different image classes now. You then do a thing called the Gerchberg Iteration. And this is a mathematical process where you link the end of any line that goes into this hole or out here into this space to another line, end of a line. So you're joining ends of lines together, and this results in a somewhat spaghetti-like set of data that you fill these holes in. Why have we done this? Because in many analysis programs, you will have a line that goes in here into the hole, but the program, the calculation program, will not be able to link it, or will not be able to resolve where to link that line coming out of the hole. We know the data in there is false. We know there's actually nothing in that hole. It's just space. But for the purposes of calculation, we need to join all those lines to the end of another line so that the calculation can proceed smoothly and not collapse into some kind of divide by zero singularity. So we do a Gerchberg iteration, which I'd never heard of before I'd done this kind of technique. Kind of thing you only find out when you do the research, but you create this false data that fills in all those holes and gaps and allows us to do our calculation. So it's absolutely fantastic technique. I wonder how they got the funding to do that, because if somebody goes along saying, I want to develop a program, a system that links ends of lines to other ends of lines in a random way, I'm sure funding bodies would think, yes. So anyway, thank you, Professor Gerchberg. We then take this is back to the more simple, actually, analysis compared to Gerchberg. We take a line across the image and we get an intensity variation. You know, it's white, it's black, it's white, it's black. There it is on this kind of sinusoid. This is doing a thing called phase unwrapping. So we get this intensity versus position variation. We then take the arc sign, so we unsign the system and we turn it back into, in this case, radians. And we've got radians going from 0 to pi to minus pi, etc. And what we do is every time the system swaps between pi to minus pi, we add 2 pi to that at that point. So we've got this intensity variation, we turn it into a variation expressed in radians, and then we add 2 pi every time we get to a drop. And what does this do? It forms it into a line. Absolutely fantastic. So what does that look like? So initially, this is your data. So you do the arc sign of it and you take it back into plus pi to minus pi variations, and you get something that looks like this. You can still tell where the holes are in the data. You can still tell where the false data is, but at least you've got this system. You then go through this process of adding 2 pi onto the system, and you go from there to there. Now, this does not look particularly exciting. However, what you've now got is a series of coordinates which are based upon the position of the line. So the line in the image moves, which means that the where you get those changes in radians on the image moves with it. So you've now got a baseline to compare other images against, and from that end up with displacement. So there you go, Gerchberg, to get rid of your phase map, to make sure you've got no discontinuities in your phase map. Phase unwrapping to get up the coordinate, fixed plane to the sample, and for each point you do the calculation. And then get the displacement. From the displacement, you can calculate the strain. So I shall drop out of there for a second, and I shall go to a series of images. So what I'll show you here is the one of the nicer images from this system, and this shows the results of this analysis. Start from the beginning. There you go. As the sample is compressed, you can follow the stresses and strain buildup in the system. So this is the shear in the system. and you can see how quite rapidly those lines are developed. This is very early forms of analysis. So we'll play that again. I find this one of the more aesthetically pleasing images, mainly because you can see this definite point of shear being built up in the system well before the sample actually fractures. So that's shear. So that's quite nice, I suppose. Let's have a look at what happens in terms of X displacements. Again, the image moves through. Now you see this kind of rainbow kind of bleed here. Again, that's because that's the Gerchberg data. You know, the correlation is got false data on it, and this is material moving into the field of view. But certainly you can again see where the displacements are on a reasonably good degree of accuracy. Remember, this field of view is 7 millimeters, and so we can see where those X displacements are being developed. And of course, the final one is going to be the Y displacement. So here we're going to go with the Y displacements. Decides to open. Come on, open. And this shows the frame number, and you can see the system. Now, this black lines here, these show areas where there's cuts in the image, where the calculation still gets confused. So many of these systems in the early days were on this was the cutting edge of image analysis of its time, and you were seeing displacement with a degree of detail that previously had not been possible. So this was quite useful. So going back to the PowerPoint. It's powerful to get both composite into plane displacement. It's simple and widely applicable if you can get a grid on the image. So we go now on to speckle correlation and cross correlation in particular. This has been presented in a number of books, and this is a book about visualizing penetration, and this was done by people such as Stephen Bless, and we contributed a chapter to it looking at granular materials, which will be the subject of a lecture. Granular composites on Friday, and gas moving through granular beds on Tuesday next week. So this used digital speckle radiography, and into that specimen you introduce, in our case, lead filings, so small pieces of lead, and we have a gun barrel, and along that gun barrel we fire a projectile, and the projectile hits the target. The film cartridge. So this is all very slow build up here. And the important thing in a lot of correlation techniques is to have some fiducial markers. Fiducial comes from fair or fi, which is a Latin word meaning faithful. So these are the markers that maintain their position. They are your faithful reference points in the image. It's important to have them. Without them, life becomes very difficult. And we fire a projectile down, get an impact, and take some flash X-rays of that image. And here we have the example of a cross-correlation process. So you have a before image and a after image, viewing image depending on your speed of your camera. And from that you take a small sub area and a larger area from round about that position. So they're similar positions in the similar-ish positions in the image. And what you do is you move that one around within that field of view. In fact, if I wanted to edit this, I'd move this image slightly further over. You move this around, and from that you get a correlation. So basically, I could do this by multiplying the intensity in this pixel by the intensity in that corresponding pixel there. the next pixel by the next pixel along and just add it together. That's one way of doing it. There are more elegant ways of doing it. And then in your next calculation, you move that sub-image to over slightly to a different part of it. And you do the same calculation. And then you sum all of those intensity multiplied by intensities for the individual pixels together, and you will get a peak at some point. And that peak represents the point at which where that image has moved to. So what you've shown is this little block has moved. And then what you do is you calculate it for lots of different sub-areas in the image, and you build up a displacement map. So this used to be, from the early 90s perspective, this will be a huge computational task. From the 2021 perspective, this is a relatively simple, well-established technique, which has been developed in many areas over the years, and there are many downloads of programs which will do this for you. So it's a fairly straightforward process. This allows you to come up with a map like this where you can see the displacement, in this case the horizontal displacement, caused by the passage of this projectile through this granular material, and you're getting a full field of view. So if you said, I'm producing some waves, the waves are going through the target is causing some motion in it, where is that wave got to, and what the motion is, the motion that's being produced, you can measure it. Now this is a bullet. Okay, so there's a physical projectile going into the sand, causing it to move, causing those lead filings to move. Those lead filings are forming a background image. We're not tracking individual lead particles, we're tracking the image produced by those particles together. So it's a pattern correlation, not a point correlation technique. And you can use it to look at shock waves and wave motion through relatively complex material. So here we have a target, quite boringly in the center of the frame there, being struck by a projectile, and that's sending some shock waves into the projectile. And here we have a coin, just for reference, and our fiducial marker, and that coin is around about 10 millimeters across. So this gives you an idea of the size of the target and also the size of the projectile. Now, the projectile sends a shock wave into the target, and we can look at motion within the target. So in this image, we're showing motion along the direction of impact. And now we can start to see the shape of the wave that's being produced. We can see the shock front where the density starts to rise. We can see what's happening in the areas of maximum density, the thing that's being pushed for longest. We can look at the unshocked region. So that is the region of the compression wave. Now, if we do the correlation to look at lateral motion, we'll see lateral release waves coming in, lateral release fans coming in from the sides, eating into the shock region. So we can show now inertial confinement in the system. This system has been hit very strongly. These materials move very strongly in the direction of impact, but it has not moved laterally. It's around about zero. Whereas to the sides, material is moving out quite rapidly, big displacements from the lateral release fan. So we can actually capture the shape of the wave front going through the target to a degree of accuracy. Depends on the pixels, depends on the size of the image, etc. But we can start recording the shape of the front. Now, we did an experiment where we sent a double shock through a material, and the double shock was caused by hitting it with a plastic projectile, which was backed by a piece of metal. And from that, we sent a step pulse in. So there was a first front up to a stress level, and then from the stress level to a higher stress level. So what we were doing is sending a double pulse in the system, one stress level, then a higher stress level. So there are two shock waves going through the system. On the right there, we see the output of the system. We can see where it hasn't been shocked. And on the left here, we can see that in that region 1, this region here, there is no shock wave at all. It hasn't reached there yet. But then the displacement starts due to the presence of the wave, causing the material to be put into motion, and we get into this region 2, and that is the first shock wave going through the system. And the strain in that region is around about 5.5%. Target. And then behind it, we got this second shock wave, and it is really a much higher stress. And there we can see we've gone up to 60% strain in the sample. So we're really collapsing down that material. This material is a polymer bonded explosive, or polymer bonded sugar. It's a simulant of a polymer bonded explosive. What we've got there is this wave coming through. So now we can start to take measurements with good spatial resolution and time resolution from within the bulk of a material. So we are no longer relying upon transparent materials, and we're no longer relying on materials where we are unable to see cracks developing directly. We can now start to look at the wavefront within these heterogeneous materials in good detail. So the next step was everything I've shown so far is 2D, and the kind of resolutions you could look for was maybe 1 millimeter spatial resolution over 30 millimeters. You've got 1 millimeter over 30 centimeters and 0.1 millimeters displacement resolution. So you had a reasonable kind of accuracy, but people always want more. So if we used a couple of X-ray heads at a 60-degree angle, we could develop a 3-dimensional digital speckle recognition algorithm. And we get all 3 components of displacement through the specimen in the system. So it also increases accuracy as well, because any out-of-plane motion, which before we would not have noticed, is now included in the analysis. So we're going from just looking at everything as motion on a flat surface, we're going to do the full 3-dimensional variation. So what we have was a sample with some X-ray heads and some film cassettes. We had some lead particle layer to give us our speckled pattern within the target. And we had the projectile firing along the axis of the system. So we used some reasonably powerful X-ray heads. These are the kind of things you find on ballistic ranges. We had a cement specimen. Again, not the hugest one in the world, but fairly large. And lead shot as the speckles, lead shot being what you find in a shotgun cartridge. So small spheres of lead and a shaped charged jet, which shot into the target. And I said 10 kilometers a second. This was a particular commercial industrial shaped charged jet. They didn't like us knowing exactly what it was. So they kept that away from us and they wrapped it in a brown paper bag. However, we could see that it was actually moving around about 7 kilometers a second, but it's still a useful stimulus for this target. And that just shows the formation of a shaped charged jet. So you've got a hollow line, we've got a line cavity of inside the explosive, and the detonation wave goes down. It collapses the material and forces the jet out into the out in a line, and it's hydrodynamic, so the pressures there are so large that the metal moves very much like a liquid, and it's also been compressed quite a lot as well, so it's rather like a hot liquid jet of metal. That was the assembly we had. The shaped charged jet is in this box because they didn't like us to see it, and this is the target down below. And this is what we got afterwards. Here's the lead speckle. There's the shaped charged jet coming in. This is the cavity we're opening up, and these are our fiducial markers. Here on the right-hand side, you can see the displacement within those markers within the sample, and got 1 millimeter displacement there. So you can find that jet pushing in. It's supersonic with respect to the sound speed in the material. So that's why you've got this nice little cone of displacement. That's just 2D. But if we do the full 3D analysis, this is the shape. This is the entry point into the sample. This is the shape of the lead layer. And please notice, we're now talking an accuracy where we're going sub millimeter. And you can see that there's some forward displacement in lead because we've missed hitting exactly on the lead layer by about 0.5 millimeter or so. So we can see the shape produced by that impact within the target. So we're doing sub-millimeter displacement of a target that's tens of centimeters in size at a time resolution of around about 10 nanoseconds. So we can really capture very small motions within the target. And this kind of experiment, I think, really deserves more attention because you can start looking at the process of movement of waves through a system. You can start looking at deformation within targets of these very high forces. So you can start to get some real mechanical insight to what is happening. We also then looked at sand and what happens with penetration into sand at different velocities. So in this sand experiment, at the top, you have an example of a cylinder being pushed very gently and slowly into some sand. And down below, we have a projectile hammering its way into the sand. And what we did was we started with pushing a cylinder slowly into sand with a lead layer present and without the lead layer present. One of the things you will be asked in any conference is, did the presence of the lead make any difference? And what we see here is 3 repeats showing not so much as you would notice. There is a variation of force versus penetration depth on the system, but basically up until about 40 millimeters or so, it's not very significant. And the significance doesn't really change much with the presence or absence of lead. So looking at the X and Y displacements, we can see here low rate penetration. So we've got the vertical, we've got the motion of the system in the vertical direction. So we see some motion upwards in the sample in the sand as we push the cylinder in. This is horizontal motion here on the right hand side, and you see motion out sideways. So we can show overall the shape of displacement in the system at low penetration rate. So look at those shapes there, particularly the one about vertical motion. Look at the horizontal motion in the system. So that's at low rate. If we do that at 200 meters a second, here we find is the lateral motion is pretty similar in terms of the area and volume of material affected. But the big difference is in the vertical motion of the system, which is now very much more confined to the tip of the projectile. So there's not that bulk lifting like there was in any of the way that we've seen before. What we're seeing is more compaction of the material. So when we look at the comparison between quasi-static to dynamic effects, we see in this granular material a big change going from the material moving down the rod, down to the rod tip as it's moving up. We see the material flowing around the system here, and we see the material being trapped in this case. And in both cases, we found there was no traveling compaction wave in the material ahead of the rod. So this allowed us to ignore some of the mechanical processes because there was no evidence for their presence. So that is the end of my slideshow for today. I've managed to keep more or less on time. And I hope from this you've seen in a little bit more detail that we can start to measure things both within and on the surface of the material with a fair degree of accuracy. The other thing that is quite clear is that we have set up a group with the European Synchrotron Research Facility to look at very small volumes of material using these kind of correlation techniques. And there's also a beamline access program being developed. So as part of this collaboration with yourselves in Perm and the associated institutes, it is possible to do these kind of experiments at ESRF in Grenoble in France. And I will be in contact with Oleg, and this was a thing that was set up last year. COVID, so we haven't been able to develop it as fast as we would like, but the main thing is it is a system, it's there, and we want people to apply. So that is a key point. So that's today's talk. Friday, we're going to talk about granular composites, and that will be a shorter presentation because we can have much more time for discussion. These first three talks are very much me establishing the background of my interests and my areas, hopefully showing you some techniques which you may be used to or you may be new to, but showing you those techniques so we can have an idea of the kind of things we can collaborate on. So can I thank you all? And before Oleg says it, I'm going to say, does anybody have any questions?
Okay. Just I will try to put my face. Okay, Bill, thank you very much. Thank you very much again. And of course, I hope you have some time yes for discussion. And let me please to ask you concerning the following, because you were talking about European synchrotron facilities. It's extremely interesting for us. Why? Scientifically speaking, of course, but also we are involved in big project in Russia, concerning creation of special modules to provide research for new synchrotron facility that will be created in 2 years, not far from Novosibirsk in Siberia.
Okay.
Okay, but now we started this research because in Novosibirsk there is well-known institutes of nuclear physics.
Yes, yeah.
And just to develop methods that will be in future used in these modules, we are carrying out research with synchrotron facilities at Nuclear Institute of Russian Academy of Science, and 3 our colleagues visited in more or less regular way. And one of the main subjects now for us, it's in situ investigation of composite materials. Yes, that could be used for gas turbines in aviation. And you know that there is a very serious problem, the so-called foreign object damage.
Absolutely.
Of foreign object damage. And during several years, we're involved in the study of this problem to realize the following experiments: its impact and then fatigue. To understand the tolerance concerning this kind of loading. And of course, concerning composite materials, it's very important to understand what is the characteristic stages of damage accumulation. Yes, because in composite materials we have practically single mechanism relaxation due to the defects, due to the damage. Okay, so no plasticity practically.
No.
As a consequence, I think we could build collaboration concerning that, and probably to formulate some experiment for European facility also. I'm talking about in Grenoble, yes, European facility.
Yes, in Grenoble. So they've set up a system. So I've been looking after the explosion chamber, which only takes grams of material. It's a small system for grams of material because the fields of view we're looking at are kind of 25 centimeters, sorry, 25 millimeters by 25 millimeters. That's the kind of field of view we're aiming for, so we can really get into the micromechanics of systems. So we've got an explosive chamber, Hopkinson bar, gas gun, dropweight setups, and they're sat in front of a beam line. And we use what's called backlighting, where we deliver a number of particles into a material and cause it to basically emit X-rays very strongly, and that provides the backlighter illumination. And from that, we can start looking at cracks moving through cement. So when I talk about crack micro damage in cement materials in the last presentation, that will include some images taken from the European synchrotron facility using a Hopkinson bar as the loading technique. So we can start to track these down, but certainly composite materials and or protection, and then fatigue damage processes generally associated with damage onto turbine blades. So you have these zirconium, titanium zirconium kind of alloys, titanium vanadium zirconium systems. You can see these very slow buildup of cracks in some states after the hard particle impact. There is an airport in the south of Argentina that is built in the volcanic region, and the dust that is on that particular airfield is the same hardness of silicon carbide. So it absolutely grinds the engines with great efficiency, and does a lot of damage to engines from vehicles operating from that area. So this is a real problem, and there's people will say, sand is not that hard. I'm like, yeah, but you get sand that behaves like silicon carbide, so it really does grind in to it. So yeah, that would be a very good collaboration. There is a lot of interest in different types of composites. I'm talking about granular composites on Friday, but on fiber composites as well. Right.
Yes, it's very interesting, of course. And in the framework also with collaboration and research concerning Siberian synchrotron facility, the name is SCIF. SCIF. SCIF, yes. You could look at internet concerning readings of this. And also the part of research related to alloys, and mainly for aviation applications, but also in situ experiments combined with X-ray. It's the subject of research also. Okay. May I ask our colleagues concerning question?
Again, I think maybe it's too early or too late in the afternoon. But the main thing is, I think on Friday when we go from type of material presenting now, which is a review of older material, the things which are more novel, I hope that people find it.
Bill, I'm sorry, there is question from Alexander Belachin. He is namely involved in the study of alloys in synchrotron facilities near Novosibirsk. Please pay attention concerning his question.
Oh yes, certainly. So have we done 3D X-ray experiments on metals? No. Okay, no. But what we have done is 3D X-ray experiments on the expansion and damage of metal cylinders, looking at aspects such as friction on the motion. So shock impact, looking at friction between metals, dynamic friction, and the other one was the expansion and fracture of cylinders. So we've used X-rays for that, and we've also used high-speed photography looking around the edge, because when you expand the cylinder, we can do it in a number of ways, but we can vary the strain rates along the cylinder, and that made it particularly interesting looking for the growth of fragmentation and also for the speed of deformation and how fast that crack moved in that material. So there is some research we've published there. It's the author is called David Jones and Dan Akins, and I can dig those references out and I can pass them to Oleg and we can pass them to you. If you're talking about X-ray crystallography style experiments, we haven't done that. I have not been directly involved in those, but again, we all know people who have, so that would be talk about that. But certainly we've looked at the deformation of samples, metallic samples under impact loading using X-rays and optical velocimetry. So yes, that's done. Oh, that's available.
Okay, and let me please, Bill, ask you also concerning the perspectives, for instance, the following research. Maybe 10 years ago, we have passed joint research with GMSA concerning self-similarity of shockwave profile due to the double shock. Probably you know this exciting experiment by GMSA. The very interesting fact that first time was I'm sorry. Я не могу сейчас говорить, прервусь. Very important result by GMSA is the following, that in some scaled variables concerning stress and time, yes, particle velocity diagram, not for stress, because it was presented with the stress, yes, in some scale coordinates for different shock amplitudes, it was plotted on some universal curve. Okay, and I think it's very important concerning understanding of transition from elastic to plastic behavior, and also evolution due to the of the system from one plastic level to another plastic level.
Yeah.
You see, and if, for instance, and we published one short paper with GMSA, and according to my feeling, it's very important for understanding of nature of shock waves in plastic materials and plasticity at all. And maybe we will keep in mind that we could collaborate in this also.
Oh no, no. So I think there is again the aim is to put in energy into a system at different rates, and that will cause a different change in the kinetics and the relaxation of the system. But if the processes are of basically, if it's the same process, there should be self-similarity in the system. Whereas if other material damage processes start to become available due to the input of energy, then the similarity should change, or it should, well, not disappear, but should change. The profile should change its shape because those other processes will affect that thing. So I think self-similarity of waves is a good method for determining if the underlying physical processes are still the same.
It's exactly because for instance, Bill, if when we have the 4-power law after Swigel and Grady, yes, and the similar by the way law we have for double shock, yes, and this self-similarity, 4-power universality, means that relaxation ability or dissipation ability in the system due to the plastic flow is huge and doesn't depend on the stress amplitude, because this kind of relaxation too pronounced to be damped any increase of stress amplitude. It's my feeling.
Oh, that's good.
Mhm.
No, I think that,
Okay,
yeah.
colleagues, please more questions.
Okay.
Mhm.
Okay.
Bill, thanks a lot.
No, thank you. I'll see everybody on Friday. I hope everyone has a wonderful rest of the day. And then have a chat on Friday, and we'll talk about granular composites and take it forward from there. And then hopefully have a more involved discussion. Okay. Thank you much indeed, everybody. Okay. Thank you, Oleg.
Thank you very much. Well, thank you. Good day for you.
Thank you. Bye-bye.
Bye.